Hi everyone. This lesson is on geometric series, and we're going to learn to find the sum of a geometric series. The method for finding the sum of a geometric series is not as easy as Gauss's method was for finding the sum of an arithmetic series, but we'll do an example numerically first, and then we'll generalize to make the formula, and then once we learn the formula, we'll practice using it. So here's a relatively easy geometric series. You can see that A is 7, and then we multiply by 2 each time to get to the next term. So R is 2. And then we're gonna look at a way that they developed the formula for this. So leave some space, but we're gonna write the sum is, leave some space above, 7 plus 14 plus 28 plus ... plus 57,344. Now we're going to multiply each term in the sum by 2. So we're going to call it 2 times the sum. And the reason we chose 2 is because it's our value of R. Okay? So if I multiply 2 times 7, it's 14, but I'm not going to put the 14 above the 7. I'm going to put it over here, because you'll see what we do next. And then if I multiply 14 by 2, I'll get 28, and so on, and so on, and so on. Eventually, I'll get 57,344, and then my last term will be, if I multiply 57,344 by 2. And that will give me 114,688. Now, if you remember a little bit about elimination from grade 10, so we're going to take these two and subtract. So 2 times the sum of the series minus 1 sum of the series just gives me the sum of the series. And this would be like having a 0 here. So 0 subtract 7 is negative 7. And now what happens here is 14 minus 14 is 0. 28 minus 28 is 0. All of these will cancel out except for this last one because we'd be subtracting 0. So we can get the sum by just adding negative 7. And there was our 114,688, so I'm just going to subtract 7, and that is the sum of all the terms in that series, in that geometric series. So that's if we add 7 and 14 and 28 and 56 and all of the terms together. Okay, so the sum gets bigger and bigger as we keep adding the terms together. All right, so now we're going to generalize this to find a formula for the sum of a geometric series. So again, leave some space on the top, and first I'm going to write the sum out as A, so the first term. The second term, remember terms in a geometric sequence are found by doing A times R to the n minus 1. So A, it would be the first term. Term 1. Term 2 would be A times R to the 2 minus 1, which is just 1, plus A times R to the 3 minus 1, which is 2. Okay, so we're following that pattern. Plus ... plus eventually the last term we know is A times R to the n minus 1. That's the sum of the first n terms of a geometric series. So notice that we're adding the terms. So now I'm going to multiply each term by the common ratio R. So above here I'm going to write R times the sum. So if I multiply A by R, I get A times R, and I'm going to put it again above the corresponding term here. And then if I multiply AR by R, I'll get AR to the power of 2. Eventually, in my series, I'll get AR to the n minus 1. But then I have to multiply, I'll show you that down here, or on this board here. If I multiply A times R to the n minus 1, by another r, I'm actually multiplying powers here with the same base. And there's like an invisible 1 there. So I keep the a, and then when you multiply powers with the same base, you keep the base, r, and then you add the exponent. So it would be n minus 1 plus 1. And then that just gives me a times r to the power of n, because negative 1 plus 1 is 0. Sorry, make sure you can see that. Okay, so that's going to be the last term when I multiply the sum, each term in the sum by r. So if we go back to our paper here, then I also have to add the last term. When I multiply every one of these terms by r, I'll get a r to the power of n. And then again, I'm going to subtract these. So I have r times the sum minus the sum on the left side. And then here I have like 0, subtract a is negative a. AR minus AR is 0, AR squared minus AR squared is 0. All of these will end up being 0. But here it will be plus a times r to the n. Okay, and we want to get the sum by itself. We want to have a formula for the sum. So on this side, I'm going to common factor out the sum. So if I divide r times the sum by the sum, I just get r. And if I divide the sum by the sum, I'll just get 1. Okay? And then here, I'm going to common factor out a because both of these terms contain a. And I get negative 1 plus r to the power of n. And then before I divide by r minus 1, I just want to flip this around because it gives us a formula that's easier to remember. So I can change negative 1 plus r to the n to r to the n minus 1. I'm just putting the terms in a different order. R to the n is still positive and 1 is still negative. And now I'm going to divide both sides by r minus 1. And I get that. So those cancel. So the sum for a geometric series is a times r to the n minus 1 over r minus 1. So that's the sum of the first n terms in a geometric series. If a is not a fraction, I use my formula this way. But if a is a fraction, I would use my formula. We can also call it Sn, or the sum of the first n terms. And I'd leave my a out front, times, and so we just have our 2-layer fraction here, r to the nth minus 1 over r minus 1. So I would use this version if a is a fraction, and I would use this version if a is just an integer. Okay? And you'll see why when we go through some examples. So there's our formula. All right, so starting with our first question, determine the sum of the first 10 terms of each series. It doesn't state that it's geometric, and that may happen on your culminating activity, so you'll have to figure it out by looking at how you get from 6 to 24. First of all, we know it's a series because we're adding the terms, and it's not just commas. Like a sequence would be like 6, 24, 96, ... And the difference is that a series, we're adding up all the terms, not just finding them, okay? So, and also it says to find the sum, not just the 10th term, okay? We want the sum of the first 10 terms. So I might write down my formula. So Sn equals a times r to the power of n minus 1 over r minus 1. And then I might pick out some of the things that I know. So I know the first term is 6a. R, the common ratio, so I could do 24 divided by 6 is 4, 96 divided by 24 is 4. I see that to get to the next term, I multiply by 4. And then they give me n. They want me to find the sum of the first 10 terms. So S10 is going to be 6 times 4 to the power of 10 minus 1 over 4 minus 1. And I want my calculator to do most of the work for me, but I do know that 4 minus 1 is 3, and then I can go to my calculator. So watch me type it in. So here's a calculator. So we've got 6 times bracket 4 to the power of 10 minus 1 closing bracket, so that's the numerator, divided by 3. And that gives us 2,097,150. So that's adding the first 10 terms, and remember, a geometric series grows quickly. 4 to the 10th even itself would be a big number, okay? And then we're adding all of the terms together. So that's the sum of the first 10 terms. All right, so here's our next one. We also want the sum of the first 10 terms here. So in our case, A is 24. R is negative 12 divided by 24, which is negative 1/2. Oops, I ran out of room there. So one thing we can do if we get a common ratio that is a fraction is we can first find the 10th term in the series and then turn the series around again because it will have the same sum. So my first step might be, so step 1, find the 10th term. And then we go back to our sequences and series formula for a geometric sequence, a times r to the n minus 1, and we're finding the 10th term. And that's going to give me 24 times negative 1/2 to the 9th. Which, so negative, remember the 9 applies to the negative 1. Negative 1 to the 9th is negative 1, times 24 is negative 24. And 2 to the 9th I would need to do on my calculator, 512. And I know I can divide each of those by 12, which is going to give me negative 2, 512 divided by 12. Nope, can't divide by 12. But I can divide by 4. So that's going to give me negative 6 over 128. I can still divide by 2 on top and bottom. So it's going to give me negative 3 over 64. So now I know that the last term is going to be minus 3 over 64. And at that point, I can turn my series around, and I know that I can change it so it's negative 3 over 64 is my first term, A, and then it would be plus dot, 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 and then minus 3. Remember the sign goes next, and then plus 6, and then minus 12, and then plus 24. So that series is going to have the same sum as if we added them all in this order as if we add them all in that order. That doesn't matter. But we can use this formatting for our formula, sorry, right here. And it'll just make the calculation a bit easier for us. So we're going to use this formatting when A is a fraction. So in this case, the sum of the first 10 terms is going to start with my A, which is negative 3 over 64, times, so now that I'm going in this fashion, I can see R is negative 2 instead of negative 1/2, So I've got my negative 2 to the 10th minus 1 over negative 2 minus 1, r minus 1. Okay? So now I've only got a 2-layer fraction here. I don't have a fraction for r in the numerator and in the denominator. It just makes it a lot easier to calculate. So I'll just keep the negative 3 over 64 out front for now. And then I'll go to my calculator and type in negative 2 to the power of 10. And that gives me 1,024. Minus 1, actually, I can just subtract 1 in my head. That would be 1,023 over negative 3. Oops. And sometimes you get lucky. I see here that I'm multiplying the top by negative 3 and the bottom by negative 3, so those negative 3's will just cancel out. And I'll get the sum of the first 10 terms is 1,023 over 64. And that makes sense because some of our terms are positive and some of our terms are negative as we're adding them, and we're getting smaller and smaller terms as we go. Okay? All right, so the next question, determine the sum of this series. So as soon as I see that the terms are getting smaller, I'm going to turn it around. That's my first step, because I want r to be not a fraction. So now I know a is 1 over 256 because I turned my series around because it's still going to have the same sum. And now r would be like 16 divided by 8, which is 2. Very easy r number. But I don't know how many terms are in the series. And I need to know that because in the formula for the sum of the series, I need to know n, the number of terms in the series. Okay? So to find n, I go back to my sequence formula. So first we're going to find n here. Step 1, find n. So then I just go back to my geometric sequence formula. And I know that the nth term in the sequence is going to be 16 if the first term in the corresponding sequence is 1 over 256. And then I know r, the way I've turned my sequence around, is 2 to the n minus 1, and n is what I'm interested in finding. So first I want to get the exponential part by itself. So I have to undo this multiplying by 1 over 256, or dividing by 256. So I'm going to multiply both sides by 256. So I'm going to do 256 times 16. And I get 4,096 is equal to 2 to the power of n minus 1. And now that's an exponential equation. So I know that I've got to be able to write this side as 2 to the something, and that's going to be a whole number because n has to be a whole number in a sequence or a series. So I'm going to try 2 to the 12th, for instance. Oh, I got it on the first try. And now that the bases are equal, I know that the exponents must be equal to solve this exponential equation. So therefore, 12 is equal to n minus 1. Add 1 to both sides, and we get that there's 13 terms in our series. So first step was to use the sequence formula to find out how many terms there were. The second step is now to find the sum. So we know there's 13 terms, so S, I'll write Sn out because we're not quite used to using this formula yet. A is going to be a fraction, so we're going to use this version. And then it's going to be sum of the first 13 terms, where A is 1 over 256 r is 2 to the 13th minus 1 over 2 minus 1. So I'm going to keep my 1 over 256, and then I'm going to do 2 to the power of 13 minus 1. So 2 to the power of 13 is minus 1, 8,191, and then 2 minus 1 is just 1. Multiply the tops together, multiply the bottoms together, see if you can reduce, but you can't. So that is going to give you the exact sum there of the first 13 terms, or of the series, sorry. So that's how much this would add to. And you can see what that is approximately if you're interested by just dividing by 256. So it's approximately 32, because I got 31.99 if you added all those terms up. And you can see that makes sense because we keep getting smaller and smaller by half each time. All right, so here's a word problem. At a fish hatchery, fish hatch at different times, even though the eggs were fertilized at the same time. The number of fish that hatch on the nth day after fertilization can be described by this geometric sequence. Notice we're starting off with a sequence here, commas, we're not adding them. And it just says, the first question, part A, says, how many fish hatch on the 10th day? So this is a geometric sequence, so just to find out how many hatch on just one of the days, the 10th day, we're going to use the sequence formula. And remember, it's important you know the difference between a sequence and a series. The commas show a sequence and the addition signs show a series. So if I want the 10th day, term 10, A is 2, R again, you divide, so I could do 10 divided by 2, a term divided by the term directly before it is 5, so times 5 to the n minus 1, so the exponent would just be 9. So term 10 is going to be 2 times 5 to the power of 9, which is a lot of fish. So what do we have there? 1, 2, 3. So 3,906,250. So therefore, 3,906,250 fish hatch on the 10th day. Part B of the question say how many fish have hatched altogether during the first 10 days. So now we want to add up to plus 10, plus 50, plus all the way up to that 3 million number there, okay, which I can't fit in writing. But I want the sum of the first 10 terms. So S10 is going to be, and we're going to use this format because A is a integer. So we can just use this formatting here. So A is 2. So 2 times R is 5 to the power of 10, subtract 1. And remember, this subtract 1 is not in the exponent like it is up here in our sequence formula, over R minus 1, so 5 minus 1. So then I would go to my calculator here and figure out what 5 to the 10th minus 1 is. And that's 9,765,624 over 4. So I'm going to take that number, multiply by 2, divide by 4. Especially in a word problem, if you end up having to round an answer, that's usually fine. But this one works out perfectly. So that's 4,882,812 fish hatch over the first 10 days. And there's our 10th term. This one's bigger. So therefore, 4,882,000. That was 812 fish hatch over the first 10 days. So that's adding the fish that hatch on the first day, second day, third day, fourth day, all the way up to the 10th day. Okay. Determine the exact sum of the first 11 terms of the series. So again, I would be saying that I want to figure out R. I know we're decreasing. So if I did negative 36 over 108, I would get, because I can divide top and bottom by negative 36, negative 1/3. So I know that I want to turn my series around before I find the sum, but I don't know what the 11th term is. So my first step is going to be find term 11. Okay? So I use my sequence formula to find the 11th term. And that's going to go right here. Okay? So T11 is going to be my A, which is 972, times my R, which is negative 1/3 currently. And that's why we're going to switch our series around to the 10th. So got 972. Negative 1 to the power of 10 is going to be positive 1. And 3 to the power of 10 is 59,049. And then I want to see if I can reduce that. I know that this is 3 to the power of 10, so I know 10 3's go in here. I want to see how many 3's go into 972. So I'll divide by 3, divide by 3 again, divide by 3 again. So I've divided by 3 3 times so far. Divide by 3 again, 4 times, divide by 3 again, 5 times, and then I know I can't. So I can divide by 3 5 times, or I can divide top and bottom by 3 to the power of 5. And that will give me term 11 in a way nicer format. So when I type this in, watch me here. So 972 divided by bracket 3 to the power of 5 is 4. And then similarly, 59,049 divided by bracket 3 to the power of 5 is 243. So a much nicer fraction than that unsimplified one. If you have a fraction button again, remember, I think this one has one, so I'll show you here. So I could type in 972 over, so that's the AB over C button. A, B over C, your fraction button. Or some people have a fraction button that looks like this, where they have like an actual box over box button. Mine doesn't have that. Over 59,049, and then press equals. And you can see on the calculator, it shows 4 over 243. Okay, so take advantage of that technology if you have it. So now I know that that's going to be the 11th term, and I only need to find the sum of the first 11 terms, or the last term in my series. So now I want to turn my series around so that 4 over 243 is my first term, and then they get bigger and bigger. So I wanted to put plus 36 there, but then I realized that the 36 is negative. So it's minus 36, make sure the sign goes with the term, plus 108, minus 324, plus 972. Okay, so I know there's 11 terms, and I know my first term's a fraction, so I want to use this format here where the fraction's out front, and my R is going to be -3 instead of -1/3, because if I do 972 divided by -324, I'm going to get R is -3. So for my new series that I turned around, my A value is 4 over 243, and my R value is -3, which are nicer to work with in that formula. So Sn equals A R to the power of n minus 1 over R minus 1. So sum of the first 11 terms is going to be A, which is our 4 over 243, times r, which is -3, and when I'm putting -3 to an exponent, you need brackets around the -3, and that's to the power of 11 minus 1 over -3 minus 1. So I've got 4 on top here, and then I'm going to go to my calculator to figure out what -3 to the power of 11 minus 1 is, and that's -177,148. And then on the bottom, for now, I'm going to leave this as 243 times -3 minus 1 is -4. And again, here I've got two negatives, so I know they make a positive on the top and bottom. And I also see I'm multiplying by 4 and also multiplying by 4 in the denominator, so those 4's can divide out. So I'm left with 177,148 over 243. And I can check on with my ABC button whether that's going to reduce or not. So I can type in 177,148 over 243, and that gives me a mixed number, 729 and 1 243rds. But if I want that as an improper fraction, I just hit Shift and my fraction button again, and you can see that it's the exact same fraction, so it can't be reduced. So this is the exact sum of the first 11 terms of that series. And we can see what that is approximately. And see if it makes sense in our mind. So 177,148 divided by 243 is about 729. And you can see that we alternate terms. So we're not just adding all the time, we're subtracting sometimes. So that makes sense. Okay, and then another one to try here. This time, we want the exact sum of the series. Oops, I realized that I didn't put plus signs in here, which I will fix, so they should be there for you guys. And this should be plus. Okay, I will fix that. So a series, remember, you're adding terms. All right, so in this case, our series, we don't know how many terms are in it, okay? And we want to flip it around. So we've got 8 over 81 plus ... plus 52,488 plus 157,464 plus 472,392. And turning it around again, our A is a fraction, but our R won't be. Let's see what our R is. So I can take one term as long as I divide by the term directly before it. So 157,464 divided by 52,488 is hopefully a nice number. So 157,464 divided by 52,488 is 3. Okay, so now I need to find the number of terms. So my first step after I've flipped it around is to find n. And this corresponding sequence is going to have the exact same number as the series would have terms in it. So we use our sequence formula for a geometric sequence to figure out how many terms are in our series. So our last term, the way we've flipped it around, is 472,392. Our first term is 8 over 81. R, when we flipped it around, is 3. And n is what we're looking for. So first thing I want to do again is get this exponential part by itself. So in order to do that, I'm going to first multiply both sides by 81 to undo this divide by 81, which is going to give me a really large number. On the left side, 81 times 472,000 392 gives me 38,263,752, and that's 8 times 3 to the power of n minus 1. I still want to get the exponential by itself, so I'm going to divide both sides by 8 now. So I'm going to leave that number in my calculator, divide it by 8, and I get 4,782,969, and that has to be 3 to some power here. So I'm going to try stuff. 3 to the 10th, bigger than that. 3 to the 12th, bigger than that. 3 to the 14th. There it is. They match. So this is 3 to the power of 14 equals 3 to the power of n minus 1. And now that I have the same basis, the exponents have to be equal. So therefore, 14 is equal to n minus 1. Add 1 to both sides, and we get n is 15. So our second step is going to be to find S15. So our a is a fraction, so we're going to use that format where a sticks out front. So our a is 8 over 81 times r, which is 3, to the nth minus 1 over 3 minus 1. So the sum of the first 15 terms is 8 over 81 times, so 3 to the power of 15 is pretty huge. 360 gets 14,348,907 over 2. I know that 2 goes into 8 4 times, so my numerator is going to be 4 times 14,348,907 over 81. And then I can check on my calculator and see if that's going to reduce. So 57395,628 over 81 equals goes in evenly, which So let me think about that for a second. I think I might have typed something in wrong here, so let me try again. 3 to the power of 15 minus 1. Oh, I didn't subtract the 1. So that was just 3 to the power of 15, and that's why it worked out. So times 4 is going to change this to 57395,624 over 81, and then that does not reduce. I'll show you on my calculator. So 57395,624 over 81, and then it shows you a decimal there. So that's our answer. You could try dividing, I know 3 goes in, you could try dividing by 3, which I think I did. And you can't, you already get a decimal, so that's your exact answer. And see how it says exact sum? That's why we have to do all this work with fractions. Okay, so that is today's lesson. And then complete the practice questions on solutions are posted. Okay? All right.